Hello everyone, in this video I will show you how to write LED blinking program for 8051 microcontroller using assembly language programming, right? So in the earlier tutorial that I have shared with you, I have shown you how to write the LED blinking code using C programming approach. In this case I will be explaining you the assembly programming way of doing the same job, right? So we have port 2 where LEDs are connected, right? Port 2 has 8 pins ranging from P2.0 to P2.7. So we have 8 LEDs connected to port 2, right? And what we want is to blink them after every, let's say, 1 second or 2 second delay, right? So first of all, it is very important to understand what is the sequence of events in this particular program, right? So first of all, what you need to do as a programmer is to make a rough flow of information that you need to code, right? So you have to make all the state of all the pins of port 2 low initially, right? So make port 2 pins low. This is what you will do initially. Then you will call a delay subroutine, right? Call delay subroutine to give some delay, right, depending upon the requirement. Then the next step would be make the status of port 2 high, right? You make them high, and then you again call some delay, and this entire code has to be the part of the infinite loop, right? So it has to repeat after the time delay, right? Or maybe if you have this sequence of event, automatically your delay is introduced over here. So you will have port 2 becoming low, then it remains low for some time, then it becomes high, it remains high for some time, and then again the sequence is going to repeat: low, delay, high, delay. And if you have LEDs connected to port 2, you will actually see the blinking of the LEDs, right? So we have to code this sequence of events using assembly language programming for 8051 microcontroller, right? So an important point to note is that the C file that we have created in our earlier tutorial was having an extension of .c, right? For assembly, the extension of the file will be .asm, right? It signifies the assembly file, right? .asm. So whenever you will be creating the file on Keil IDE, you have to save it with .asm extension, not .c. So you don't need to use .c, you have to use .asm because it's an assembly file, right? So the steps more or less will remain the same as I have explained you in the earlier video, but the only change that will come will be here. When you will create a new file, we will have to save it in .asm format, not the .c format, because here you are coding it in assembly language, right? So this is the flow that we have to code, and now we are going to code it using assembly language. So for 8051 microcontroller, the assembly language programming has certain rules, certain instructions, certain assembler directives that you must know. So without going into the details of that, I will just make sure that you guys get a clear indication of the flow and understand each and every instruction as it is coming in the code, because that is one of the easiest way of doing it, because here you will be analyzing this example and trying to see what all instruction and directives we are going to use for achieving this particular blinking LED task, right? So every assembly program is going to start off with assembler directive org. So you write org 0000h, the starting location from where your program is going to start. H signifies the hexadecimal format, right? And then you jump onto a label. So you can name anything. I'm using main as my label name, so I'm willing to jump from this position to the label main, right? So my control is going to jump to the main is the label, and when you create a label, you do something like this. Colon sign is going to come over here. So this is a label. Now you write some instruction over here. The first thing which you have to write is make the state of port 2 low. So move p2 comma hash 00h is what you need to write for making it low, right? Hash indicates that it's immediate addressing, 00 is the value, h signifies its hexadecimal format. So a quick understanding of this entire thing is required over here. You're writing 00h, right? You're writing 00h, it's hexadecimal format, right? So this signifies 4 zeros, 1 2 3 4, and this again signifies 4 zeros, 1 2 3 4. this will be the state of P2.0 and this will be the state of P2.7 and so on. So you can see all the pins of port 2 will be 0, right, by writing this instruction. So it's hexadecimal format that we're using. Now this is done. Now we have to call a delay subroutine. So we will be using an instruction called acall. Acall is the name of the instruction, and then we will be writing acall delay, right? This is how we need to write the delay subroutine, right? Then we have to make the status of port 2 as high, so we'll be writing move p2 comma hash 0ffh, which means make the state of all pins high. Now in this case you are writing ff. Whenever you're going to use a, b, c, d, e or f, then you have to make sure that you put 0 over here before using those, right, those things. So f, h, this f signifies 4 ones and this f signifies again 4 ones, and this is p2.0. this becomes the state of p2.7, and that's how it is. So this indicates that the state of all the pins of port 2 will be high, right? So we are done with coding this particular thing. Now we have to again call the delay subroutine. So we'll say a call delay, right? So this is going to call the delay subroutine again, and then everything has to be in a loop, and the simplest way of doing this is to use this instruction again. So you will be using sjmp short jump main, right? So now in this case, what does it mean? Jump to the main label. So this is your main label. Writing this means you are jumping back here, and then entire sequence of events is going to repeat, right? So you have coded what exactly is written over here. So you made the state of port 2 low, you called a delay subroutine, you made the state of port 2 high, you again called a delay subroutine, and then you have put everything in a loop using sjmp main, right? So everything is gonna repeat. So we are done writing this part. Now the most important point in this particular case is the delay. How to generate the desired delay in assembly. We have seen how we can use a for loop in C language for generating the desired delay, and now over here you have to see how you can generate a desired delay value using assembly language programming approach, right? So my next step would be explaining you how to generate the desired delay, and then combining the delay code, the delay subroutine code with this particular section that we have written over here, so that you can have the complete code ready with you for achieving the task of blinking the LEDs which are connected onto the port 2, right? So I will now explain you how to generate the desired time delay using assembly language programming approach, right? So now we will be coding the delay function. So for generating the delay, the desired delay, you have to understand certain points, right? So the first thing which you must have understood through the architecture study of 8051 microcontroller is that it has got resistors ranging from R0 to R7. They are general purpose resistors. They are of 8-bit length. So the maximum value which they can store is like 2 raised to the power 8 minus 1. So it will be 255 in decimal, right? So this is the maximum value that these resistors can store, right? So we are going to generate some delay, right? So first of all, you must understand that for every one machine cycle, right? So every one machine cycle, you will have time delay of close to, let us say, 1 microsecond, right? So approximately it is 1 microsecond. It strongly depends upon the crystal frequency that you are using. In case you are using 11.0592 megahertz crystal frequency, then it will be close to 1.085 microseconds, right? The time delay, because when you say the frequency of crystal oscillator, let's say it's 11.0592 megahertz, right? So you do 1/12 of the crystal frequency, right? 0.592, and then whatever the result is, you take reciprocal of that, right? So you take reciprocal of that, then the result will be close to 1.085 microseconds, right? So we can say it is close to 1 microsecond delay that every machine cycle is going to take, right? So we are going to use an instruction which is DJNZ. This signifies decrement and jump if not 0, right? This is what it means. Now this DJNZ instruction is a 2 machine cycle instruction, so it's a 2 machine cycle instruction, right? So whenever I'm going to use a DJNZ instruction, it's going to have 2 machine cycles, so it will be like 2 microseconds, right? So in case I load my resistor, let us say any of these resistors, let's say R0, if I'm going to load R0 with a value of, let us say, 250, if I load my R0 with a value of 250, like move R0 comma hash 250, what does it mean? It means R0 will be having the value of 250, right? So this R0 will be having a value of 250. Now I'm going to write one instruction, let's say like this. If I write DJNZ R0 comma A1, A1 is a label. If I put A1 label over here, what does it mean? This instruction has to be properly understood before moving further. This says that decrement and jump if not 0, the contents of R0, right? And check if it is not 0, then jump to the instruction which is having a label of A1, which means the same instruction. A1 is a label which we have put in front of this instruction, right? So what does it mean? That it is decrement and jump if not 0. So decrement the contents of R0 by 1. So R0 content has to be decremented by 1, and the result will be again in R0. This instruction is going to check whether R0 is 0 or not. If it is not 0, then the control is going to jump onto the instruction which is having a label of A1, which means the same instruction, right? So I've loaded R0 with 250, right? So R0 is loaded with 250, which means that when it's going to run for the first time, 249, 248, 247, 246 and so on. So one DJNZ instruction is taking 2 machine cycles, which means 2 microseconds, and this is going to repeat for, let us say, 250 times. So it will be close to 500 microseconds of time delay, right? If I am going to have one more instruction, let us say, where I have loaded R1 resistor, let us say, with the same value of 250, using similar instruction, move R1 comma hash 250, and if I write same thing, DJNZ R1 comma A2, and if I put A2 over here, it again is going to give you a time delay of how much? It is 2 microsecond multiplied by 250, so it will be again 500 microsecond, right? And if these 2 instructions, they're going to be used one after the another, you will be having a time delay of 500 microsecond into 2, which means 1000 microseconds, which means 1000 microsecond, and this 1000 microsecond indicates that it is 1 milliseconds of time delay. This is 1 milliseconds of time delay, right? Is this clear? This entire sequence of event. What I've done is I've just explained you that there are certain resistors R0 to R7. They're gonna store 8 bits of data, and maximum value which it can store in decimal is 255. One machine cycle is close to 1 microsecond. It strongly depends upon the crystal frequency. If you're gonna use 11.0592 megahertz crystal, then you do 1 by 12th of the crystal frequency. The time is gonna come over here, some value. You take reciprocal, the frequency is gonna come over here. You take reciprocal of that, you will have the time. The value is gonna be close to 1.085 microsecond. I can take it as 1 microsecond. There is a special instruction DJNZ, decrement and jump if not 0. It's a instruction which is gonna consume 2 machine cycles. So we will be having a time delay of 2 microsecond. If I load R0 with 250 by using this kind of an instruction and use DJNZ R0 comma A1, this entire process says that you will generate a delay close to 500 microsecond. Again, if you're gonna use the same sort of thing for R1, you will have again 500 microseconds of time delay, right? So if you use them one after the another, 1000 microsecond, which means 1 second. So a code which will have this kind of a thing is going to give you a delay of 1 millisecond. 1 millisecond is too small a delay to actually see the blinking effect of LEDs, so we have to make sure that we increase it by using loop inside a loop kind of a thing, right? So we'll make it 1 second, right? So now I will show you how this entire thing can be repeated, loop in a loop kind of a way, so that you can achieve 1 seconds of delay. I hope this is clear, this delay part. Let's move further and let's see how we can develop 1 second delay. So now in this case, our objective is, let's say, is to generate a time delay of 1 second, right? So let me straight away code something for generating the time delay of 1 second. So let us write something like this: delay, and now you load something into the registers. Move, let us say R0 comma hash 4. The second instruction which I'm gonna put is, let's say, move R1 comma hash 250. Load the value of 250 into R1, right? And then let us say I'm writing move R2 comma hash 250, and then I'm writing move R3 comma hash 250, right? So this is what I have written: R1, R2, R3, all three loaded with 250, are not loaded with 4. There's a purpose for that. We'll see how this entire sequence is working. So I'm going to write one instruction. The instruction says dj nz, decrement and jump if not 0, R2 comma, let's say a1 being here. So I will be getting a delay of close to 500 microseconds from here. I'll be writing dj nz R3 comma a2 is over here, so again 500 microseconds over here. Now I'll be putting up again one dj nz instruction. So it says dj nz, and I will say R1 comma a3, right? R1 comma a3. So a3 label becomes the part of this, right? So how this entire thing is working: you load R2 with 250, R3 with 250, decrement R2, if it is not 0, stay here, decrement R3, if it is not 0, stay here. So now we have this instruction dj nz R1 comma a3, right? So what does it mean? It means that decrement R1 by 1, check if it is 0 or not. If it is not 0, go to A3. A3 is here. You load again R2 and R3 with the desired values, and again get the delay through dj nz, right? So this is what this entire sequence is. The time R1 becomes 0, right? Because R1 is 250, I will use another instruction dj nz R0 comma A4. A4 is the label which we are gonna put here, right? So now in this case we are decrementing R0 by 1. R0 is initially 4, now it becomes 3, it is not 0, go to A4. A4 is here. Now R1 is again going to be loaded with 250, and this entire process is going to be repeated. The time R0 becomes equal to 0, we are gonna get out of the loop using return statement, RET. RET is return, which means whatever delay we wanted to generate, we have done that, right? So what is the time delay which we are going to get? Look, this entire sequence was giving you 500 microsecond. This entire sequence was giving you 500 microseconds. So it was 1 millisecond combining together. You are decrementing R1 by 1, going back and going back over here, again getting this. What is the value that you have stored in R1? That is 250. So you will have 250 times this entire loop is repeating. This loop is giving you 1 millisecond delay, right? If we consider only this one, so it will be 250 milliseconds. It is 0.25 seconds. All right, is this clear? So this part was giving you 1 millisecond. This count value in R1 is 250. So this loop, because of this instruction, is repeating 250 times. So you'll be having 250 into 1 millisecond, 250 milliseconds, which is 0.25 milliseconds, right? Now when you see this part, this instruction, the R0 value was 4. So this entire loop starting from here, starting from this point to this point, this is repeating how many times? 4 times. So you will be having this delay which you are getting from the inner loop multiplied by 4. So your count is 4, your inner loop delay was 0.25 seconds, so you multiply it by 4, it will be 1.0 seconds. So this entire routine is going to give you the time delay of close to 1 second, right? So this is how the delay subroutine has to be written. And now when you see this code that we have created earlier, this was the code, the delay function wherever we have written, this is what the delay function that we want to write, right? And the program has to be ended by using end at the last. End is what you have to use because the program has to be written between org and end, right? So this entire program is going to be used for blinking the LEDs which are connected to port 2, right? I hope this entire delay calculation is clear to you guys. Now let us write this code on Keil and run it and try to see the output on the hardware, right? So this is something which we are now going to analyze on Keil IDE and on the hardware. So let's see these parts, right? So here is the final code for LED blinking using assembly language. It is now quite clear that how the delay is going to be produced using delay subroutine, and we have calculated it very well that using this particular delay subroutine we will be able to generate a delay of close to 1 second, right? So quickly checking out the program, it starts off with org000h. You jump to the main label, this is the main label, you clear the state of port 2, right? So which means this instruction indicates that clearing P2, right? So all the pins will be having 0 value initially, then you call the delay subroutine. For the amount of delay that we have introduced through this delay subroutine, the state of port 2 pins will remain at logic low. What we have done, we have now made the state of all the pins of port 2 as logic high. So making all pins of P2 go to logic high, right? So now all the pins of the port 2 will be taken to logic high, right? Because we have moved the value FFH into port 2. FFH means F indicates 4 ones and another F means another 4 ones, right? So this is a binary equivalent of FFH. So this indicates clearly that all the pins of port 2 will be at logic high once this instruction gets executed, right? Then you have again called the delay subroutine, which means again you will be having a delay of close to 1 second. So for 1 second the LED will remain in the on state, and then you have used SJMP instruction with jump to the label main. You will jump to the label main and then the process is going to repeat again. So which means port 2 state will be cleared and then it will remain at low level for the amount of delay which we have introduced, which means for 1 second again it will be low, it will be becoming high in this line, remaining high for 1 second, and then again jumping, making it low, remaining low for 1 second, making it high, and then remaining high for 1 second and repeating the process again. So this is how this entire code operates. Once delay subroutine is called, this entire set of code is getting executed. You are getting a delay of close to 1 second, and once this return instruction ret gets executed, you go back to the next instruction, right? So it gets shifted over here once you call delay from this position, and then when this is called from line number 8, then in that case once it gets executed return, then it shifts back to the next instruction, which is SJMP main, and then the process again executes, right? So this is how this entire code is executing, and needless to say every assembly program has to be written in between org and end.
So that's the reason why end is at the last, Virgio is at the top, right? So now quickly check the output on the Keil IDE. So for doing that, I will just quickly compile the code. So I'm building it, there's no error, no warning. I'll go to debug, I'll click on start stop debugging session. This is the state of port 2 initially. I'll go to debug and I will click on run, and you will see the state of port 2 changing from FF to 00 and so on. So 00FF, 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 and it's gonna repeat again and again because the entire set of code has been written as a part of infinite loop, because we have used SJMP main instruction, which is going to repeat the entire set of code that we have written over here, right from line number 5th to line number 8th. This particular set of lines will be executed infinitely, right, because of this SJMP main. It's like while one for a C program, right? And you will see that the LEDs which are connected to port 2 will be blinking after every 1 second, right? So the code is looking perfectly fine. Let us now analyze the output on the hardware by uploading the hex file that we have created for this code onto the development board, and see the state of LEDs, whether we are able to get a blinking pattern on port 2 or not, right? So LEDs are going to be connected to port 2, and because of this changing state from FF to 00 with the delay in between, you will see the blinking effect, right? So the next step would be analyzing the output on the hardware. So I will stop the execution of this code. I'll go back to the main IDE screen. So we are back here. Now the next step would be uploading the hex file on the board. Let's do that part, right? So now let us upload the code for LED blinking on microcontroller board. So you have to browse the file, and here it is. The name of the file is LED_blink, right? So we just need to press this start button, right? So I click on this, attempting to connect, and now programming is started. It is finished now. So we have successfully uploaded the code for blinking the LEDs, and now let's see the output on the hardware. So here is the development board, and this is port 2, right? And I have the connector cable. One end of the cable is now connected to port 2. The other end of the cable, I'm connecting it onto the LED section, right? So here it is. You can see the LED is blinking. It remains high for some time. It goes to the off state. It remains in the off state for some time, and then the pattern is repeating. This is what we have written, and we have achieved exactly the same thing, right? So this is how you can achieve LED blinking using assembly language programming on 8051 microcontroller. So I hope you have understood the concept of interfacing LEDs as well as the assembly language programming, and stay tuned for the further updates. We'll be explaining much more about other interfacings with 8051 microcontroller in our upcoming videos. Thanks a lot for watching, and happy learning.